Okay, hello everyone. I'm just making a quick video that to go over some fear response problems that are going to be useful for the test, and also I want to go over energy bar charts as well, as that's something that we covered in one of the class kicks, and hopefully we had a chance to read through this article. But I highly recommend refreshing your memory and skimming through this again. So let's just get started with the bar charts, and then I'll go through the few practice problems, and that'll be it. So anyways, so the bar chart illustrations, I would say the most important thing to remember when you're looking at a problem that involves the bar charts is, it's just like how you would approach a normal conservation of energy problem. But something that's unique to the bar charts is showing the relative size of how the energy is distributed. So, for example, if you have a ball that's falling, obviously at the very beginning, all of its energy is in potential energy, and it has no kinetic energy. But as it begins to fall, that potential energy turns into kinetic energy. And when it's halfway down, it's going to be a 50-50 split. And then right before it hits the ground, it's not going to have any gravitational potential energy, and it should be all kinetic energy. So let's just look at some examples so we can see what I'm talking about. In the lesson on Physics Classroom, they go over the first example where you have a ball that's above the ground at rest, and then it falls down, right? So here we can see the charts that they show that at the initial state, all of its energy is stored as gravitational potential energy. And the final energy is going to be stored as kinetic energy. So the gravitational potential energy turns into kinetic energy. And something that's important, I want you to note the relative sizes of the bars, right? So here we see that this bar for the gravitational potential energy is 5 units tall, and we should have the same amount of energy at the end, because the law of conservation of energy, that holds. It's one of the most important laws of all of physics. So here, this is obviously a very straightforward example, but I want to at least go over one that's a little bit more interesting. For example, what happens when you have an external work that's acting on the system? So let's, for the sake of keeping the video relatively brief, I'm not going to go over all the details here. You can just read through it. They explain it very well. I just want to add some details for the actual problems. So let's just look at the first one. We have a ball is dropped from rest from a bridge, and as the ball falls through the air, it encounters a small amount of air resistance. The final state of the ball is the instant right before it strikes the water. So like the instantaneous moment before it hits the water, right? That's going to be where we analyze the final energy. So here, let me just go, obviously they explain it here, and they show what the initial state and the final state is. And then the bar chart is over here at the bottom. Actually, does it show it? Wait a minute. I guess you just have to physically go to the bottom. Okay, so this is the representation that they give. But I want to add some more detail, some more context, and some things you want to look out for when you see these problems in the test. So I already have a lot of it written here. So we have here, say you are given this problem as a word problem. Obviously, they don't necessarily give you a picture, right? So that's a very important skill. Whenever you have a physics problem, just draw a picture to help you visualize what's going on, and so you can understand what equations you need to use or how to approach it. And in this case, we just need to just show how the energy is distributed in the system in its initial state, and then how the energy is distributed in its final state. So initially, we know that it is at some height above the ground. It's initially at rest, and it's going to begin to fall through the air. Something that's important about this problem is that there is air resistance, but if you remember, it says that it's a small amount of air resistance. Okay, so it's a small amount of air resistance. The way you want to represent it in the chart is as shown here. We put that there's gravitational potential energy, and that there's going to be some work done by the air, and notice how much smaller that bar is than the gravitational potential energy. Something else I want to make sure we understand. So why is that bar going below the horizontal axis, right? So the idea is that the conservation of energy has to hold, right? So if we're looking at the energy of the ball, we know that the final kinetic energy is not going to equal the initial potential energy. That doesn't mean the conservation of energy is violated. What that means is that the energy went somewhere, right? So typically it's friction. Air resistance is kind of like a type of friction. It still is a resistive force that acts on an object. But it's important to note that it basically takes that energy away, right? So that energy doesn't get destroyed. It just, goes into the actual air, right? So whenever you have friction, that turns into thermal energy, or in the air itself, right? That's going to be changing the velocity of the air, or effectively the air molecules will also heat up as well. But we're not going to worry about those details. Just the fact that energy is being taken away. So mechanical energy of the ball is being taken away by the air resistance. Now, there's two ways to think about why it's negative, right? I know it seems like common sense, but it's important to understand the underlying physics. So there's two ways you can look at it. One is just by looking at the definition of what work is, right? So the work done on an object is Fx cosine theta. But another way is by looking at the work energy theorem, right? So here I write out the work energy theorem, W equals delta Ke, right? So change in kinetic energy of the ball, that's going to be the work done by the air resistance. So, obviously, if there were no air resistance, the ball would be moving more quickly by the time it hits the water. And that air resistance is effectively going to slow the ball down, right, as it's falling. Now, granted, this ball actually speeds up because the gravitational energy is turning into kinetic energy, but it would, it's not going to be going as fast as it would have otherwise, given that there's air resistance. So given the air resistance is effectively taking energy, mechanical energy away from the ball, we know that's a negative work. But also looking at the work function, let's just review this. I'm confident everyone's familiar with this because everyone did well on the quiz, and we covered it a while ago, but just as a reminder, you can look at the vectors, right? And you understand that this cosine theta bit, that theta is the angle between the vectors, right? So you look at the direction that the vectors are pointing in, and the angle between that is going to be, well, the theta that you put into the work equation. So notice I draw these two vectors here. The force of air resistance is going to be pushing up on the ball while the ball is displacing downward. So these vectors are 180 degrees apart from each other, right? So the force of air is pointing straight up at 90 degrees. The displacement is going straight down at 270. So there's a difference of 180. And we know that the cosine of 180 is -1. So that's one way to see that the work has to be negative. And then underneath it, I also drew, just some things to keep in mind. You don't have to always do the cosine theta bit as long as you understand these basic principles. So if they're going in the same direction, obviously the angle between the direction of the vectors is 0. Cosine of 0 is equal to 1. It's just positive work. So same direction, positive work. Opposite directions, negative work. Okay? And if they're perpendicular to each other, that's going to be an angle of 90 degrees. The cosine of 90 is 0. So there's actually no work done, right? So in a case where the force applied, or whatever force is acting on the system, that force is not doing work on the object if the object's displacing at a right angle. Okay, so for example, if you're a waiter and you're moving a dish from the kitchen to where the people are eating, if you're holding the plate and not changing the height of the plate's going to be displacing horizontally, but the force that you're applying is actually going straight up, right? So you're actually not doing any work on the plate. You're not changing the energy of the plate, although your arm will get tired. That in terms of the work being done on the plate, there's no work being done. It's only when you lift the plate up that you're actually doing work on the plate. So anyways, just, that's a common misconception, the fact there's no work done at a right angle. I just want to make sure that's covered. Going back to the bar chart, this was all just explanation of positive versus negative versus no work done. What's important about the bar charts is, again, you draw a picture, you identify the types of energy that are in the system, right? So we know there's gravitational potential energy, there's kinetic energy, and there's work done by the air, negative work specifically. And notice how on the, I make it different colors just to make it easier to see. But for the final energy in green, notice how that bar is shorter than the bar for the initial gravitational potential energy, right? So this is showing that that negative work that the air did, that took away energy from the ball. But if we look at the total energy of the system, right? So looking at the energy of specifically the ball, we see that energy taken away is shown on the bar chart. The final kinetic energy of the ball is less than its initial potential energy. And the reason for that is because the air resistance took mechanical energy away from the ball. So yeah, I mean, just go through the other examples. I don't want to go through each and every one because we already did it on the class kick, but just review them. And if you have any questions, just let me know. But let's actually get into the free response problems. So these are some problems that will be helpful. And I already have them set up over here. So I'm going to walk you through them just to make sure you know how to approach them. So let's see, the first one, let's say we have a spring. All right, so we have a, ooh, wait a minute, why am I, all right, let's switch that up a bit. Okay, so let's look at the first one, okay? So let's say we have a spring, all right, and it's compressed, and it has a spring constant K equal to 250 newtons per meter. And let's say we compress the spring. So the spring is compressed 8 centimeters. And there's a ball at the end of the spring. Okay, let me make that a different color just to make that clear. Okay, so this is the ball. And obviously this is a spring. I'll put a little wall here for the spring to push off of. So we know that the spring is storing some elastic potential energy, right? So because we displace the spring from its equilibrium position, it's compressed. There's energy stored inside of that spring. It's going to transfer it into the ball. Now let's say that the mass of the ball is equal to 1.5 kilograms. We need to find the final velocity of the ball. So the final velocity. Now, if this is given a word problem, you're just going to read through it, write down the key values, your knowns, your unknowns, and you have to solve for the unknown. So at this point, what we want to do is we want to identify what the initial energy of the system is. So what's the initial energy? And we know that has to equal the final energy of the system. So this is the initial energy. I'm going to make this in green, right? So this is the initial energy of the system. And all I have is actually the energy inside of the spring. So 1/2 kx squared, right? So that's the only energy I'm dealing with, elastic potential energy. So I have the elastic potential energy of the spring. I think on physics classroom they put PES, but anyways, I just want to focus on the actual equation. But yeah, so we know we have elastic potential energy at the beginning, at the very end, right? So this is the initial energy of the system. Here, let me move this. I want to draw the picture. And at some later time, right? So this is T naught. So at T equals 0, that's the initial state. And then at some later time, I'm just going to call it TF, right? The spring is no longer compressed. So I'm going to draw it stretched out to its natural length. Okay, so the spring is no longer compressed. And now the ball is traveling with some final velocity. So it has some final velocity. We don't know what that final velocity is, but that's what we're going to calculate based on the values given. So this here, obviously, this is the kinetic energy of the ball, right? So my final energy of my system, it's going to be all in the kinetic energy of the ball, which is 1/2 mv squared. So I start with elastic potential energy, 1/2 kx squared, and then I have some final kinetic energy, 1/2 mv squared. And that's pretty much it. This thing's not going up or down a hill. It's not vertically displacing. The potential energy doesn't change, right? So it's practically on the ground, so the potential energy is 0. So now let's actually set up the equations. So here I have 1/2 kx squared is equal to 1/2 mv squared. And this is just because of the law of conservation of energy. All the energy that was in the spring is transferred into the ball. Now I'm going to solve it just by doing algebra. You can plug in the numbers if you'd like. I find that students are less likely to make a mistake that way, but it's important to know how to do it with just the algebra. So one thing I can do, I notice there's 1/2 in each term, so I'm just going to get rid of that, right? So I have kx squared equals just mv squared. And then I need to solve for v. I guess I should say that's vf. So vf. And so I'm going to divide both sides by m. So I have vf squared is equal to kx squared divided by m. And then I'm going to take the square root of both sides, right? So if I take the square root of both sides, I get vf is equal to the square root of kx squared divided by m. Now, something that's very important that I can anticipate maybe a common mistake. Notice that it's compressed 8 centimeters. So we need to convert the centimeters to meters. Okay, and make sure you don't mess this part up, right? Because look at the spring constant. The spring constant is 250 newtons per meter, not per centimeter. It's per meter. So I have to convert that centimeters into meters, and I know that 8 centimeters is going to equal 0.08 meters, right? There's 100 centimeters in a meter. Centi, the prefix just means 10 to the minus 2. So make sure you are careful with your units. If they give you centimeters when you're dealing with a spring in terms of how much it compresses or stretches, make sure you're going to convert that into meters if the spring constant is in newtons per meter, which it always is. But so let's now plug in our values. So here I have the square root of k, that's 250 newtons per meter. I have the amount that the spring is compressed, which is going to be 0.08 meters. And I'm going to divide that by the mass of the ball, which is 1.5 kilograms, and then take the square root of the whole thing. And I'm even going to bust out the calculator just to make sure we don't mess this up. So here I got 250 times 0.08. Okay, divide that by 1.5. And then don't forget to take the square root at the end. Me personally, I like to just raise it by the 0.5 power. It's the same thing as taking the square root, raising it to the 1/2 power. And then with that, I get a final answer of 3.65. So the answer to this problem is 3.65 meters per second. All right. That's a pretty straightforward one. Just you have elastic potential energy going into kinetic energy, and you just solve for the unknown. So let's do one here with a skydiver. So let's say we have a skydiver opening a parachute. So we have a skydiver opens his parachute and falls at a constant rate of 10 meters per second. Let's say he falls from, all right, so I'll draw a little picture. So I got a little skydiver here. That's his parachute. Okay. And he's falling at a constant rate of 10 meters per second, right? So this is his terminal speed, right? So he's traveling with you can also use terminal velocity, but you get the idea. So he's traveling at a velocity where the force of the air is equal to his force of gravity, right? That's kind of the whole point of having the parachute is you have a large area for the air to push against, and you're going to fall at a much slower rate such that you can hit the ground and not be hurt. And at this point, we know that he's at a height of 2,000 meters. So let's say his height is 2,000 meters. And he has a mass of 70 kilograms. All right, so he has a mass of 70 kilograms. And what we need to do is we need to see how the energy is distributed in the system. So this part here, this is the initial energy of the system. I'm going to use the same kind of color scheme here. So this is the initial energy. right? So E naught, that's the initial energy of the system. The final energy of the system, which I actually draw just below because he's falling. So we're going to look at his energy at a height of, what did I put here? Oh, at a height of 100 meters, right? So we're looking at the energy, his mechanical energy from a height of 2,000 meters down to a height of 100 meters, right? So let's say he falls, down to 100 meters. I'll draw him down here. So he's just about to hit the ground. So now his height is only 100 meters. Okay, he still has the same mass, obviously. He's going down, still going down at 10 meters per second. And this is going to be the final energy of the system, right? So it's going to be EF. Okay, one thing that's important to note is there's going to be work done. So there's work done by the air resistance, right? Because if you think about it, he's traveling at a velocity of 10 meters per second. So he has a certain amount of kinetic energy. And at his final position, or at least the position we're analyzing, when he's 100 meters above the ground, right, he's lost a lot of potential energy, right? But he still has the same amount of kinetic energy. So in terms of like where did that mechanical energy go? It went into the air. So the air did negative work on the skydiver, reducing the skydiver's mechanical energy, right? So that potential energy doesn't turn purely into kinetic energy. A lot of it goes into the work done by the air resistance. So for this problem, all you need to do is just specify how much energy he has and see how the energy is split up. So we're going to look at his initial kinetic energy. So this is going to be his initial kinetic energy. We're going to look at his initial potential energy. Okay, and we're going to look at the work done by the air resistance. All right, so what does that equal? And we have to calculate. And then for the final energy, we know that it's going to be just kinetic and potential, right? So let's actually figure this out. What you're going to want to do, it doesn't really matter in what order you do it in. It's just kind of what makes sense to you. But I'll just do it in order. So let's look at the kinetic energy. We know the kinetic energy initially is equal to 1/2 mv squared. So it's 1/2 times 70 kilograms times the velocity squared. Okay. And let's just type it into the calculator. So we have 1/2 times 70 times 10 squared, which we know is 100. Just put 100 there. All right, 35,000 or 3,500, I should say. So we got 3,500 joules. That's his kinetic energy. His potential energy, well, we know the equation for gravitational potential energy is mgh. For this problem, we're going to assume g is 10. All right, so just so the numbers look nice. And I believe on the test, if they have a problem like this, it's that we're just going to use g as 10. I think it's going to be, if it's specified, just use g equals 10. Just use g equals 10. You don't have to use 9.8. So let's go through here. Again, just plug in the numbers. So the mass is 70. The acceleration due to gravity, we're going to approximate it as 10. And the height is at 2,000 meters. So we're looking at his initial gravitational potential energy. All right, and again, just type in the calculator, 70 times 10 times 2,000. And we get an enormous number, 1.4 million. So yeah, you're going to have quite a bit of energy if you fall 2 kilometers above the Earth. And hopefully you have a parachute if you do that. Otherwise, that may not end well. All right, so 1.4 million. That's how much gravitational potential energy he has at the beginning. Now, in terms of the work done by friction, or I should say by air resistance, You can just calculate it if you want. Personally, so I will calculate it, but I want to show you how there's an easier way to get it. So let's just go through the calculation. So the argument here is that we know he has a weight of 700 newtons, right? So his weight is equal to mass times gravity, and that's going to be 700 newtons, right? So 70 kilograms times 10 meters per second squared. Well, if his weight force is equal to 700 newtons, and he's traveling at a constant rate, that means he's not accelerating. And if he's not accelerating, the forces have to be balanced. So if his weight force is 700 newtons, then air resistance has to also be 700 newtons, right? So it's also 700 newtons, and it's going to be going upward, right? So let's use the equation, Fx cosine theta. Actually, I kind of like, we can use Fd cosine theta, just because you don't want to think that that x just is multiplied by the cosine theta. Wait, why? Oh, I'm on the wrong thing. All right, let's just use Fd cosine theta. Okay, so he travels a distance, that air resistance, as we're looking at this problem, the air resistance acts over a displacement of 1,900 meters, right? So if I plug that into the equation, I have a force of 700 newtons times 1,900 meters, and we have a cosine of 180 degrees. Now remember, well, I want to specify. So why is it cosine 180? Well, the air resistance is going up. The displacement, he's displacing downward. And going back to our previous example, emphasizing negative work, if they're in opposite directions, the work done is going to be negative, right? So there's negative work done by friction. Let's just calculate it. As a reminder, we know cosine 180 is equal to -1. And then I'll multiply that by the force of air resistance, which is 700. And it displaces 1,900 meters downward. So I got 1.33 million. All right, so I have 1.33 million joules. All right, now let's look at the final energy. Well, his final kinetic energy is going to be the same as his initial because he is traveling at the same speed. I'll write it out for the sake of consistency. Times 10 meters per second quantity squared. And we get the same number, 3,500 joules. Okay. The final potential energy, well, it's going to be a lot less because I put HF. This is going to be H naught. So his initial height and his final height. All right, so it's going to be a lot less because now he's only 100 meters above the ground. So again, it's 70 times 10 times 100. All right, and in this case, we get 1,000 times 70, so that's going to be 70,000. So 70,000 joules. All right, and that's pretty much it. So the thing I kind of wanted to show in terms of the work done, another way to look at it is, well, his initial kinetic energy is the same as his final. And his initial potential energy was 1.4 million, whereas his final potential energy is 70 million. So where did the rest of the energy go? It went into, oh, whoops, I almost forgot a negative sign. Make sure you put a negative sign. That is something that you want to emphasize, okay? And even I forgot it, even though I made a big deal about it. So, yeah, this is negative 1,000, right? So it's negative work done. Okay, so make sure you don't forget that. So yeah, it starts at 1.4 million joules of potential energy, and he ends up with only 70,000. So where did the other 1.33 million go? Well, that was the work done by the air resistance. And so when I was saying there's an easier way to do it, you don't even have to figure out the FD cosine theta or any of that. You understand that well, his initial potential energy is 1.33 million joules greater than his final potential energy. And the initial kinetic energies were this is the same as the final kinetic energy. And we know that energy has to be conserved. So whatever energy is missing, that has to be because of an external work being done on the system. So I think that one's simple enough, right? It's just looking at a situation, understanding what equations you need to use, and analyzing the energy of the system. And the third FRQ I want to go over is one where we have work being done at an angle. All right, so let's say we have a box and it is, there's a force applied at an angle of 30 degrees above the horizontal. So the way I'm going to do that is I'm going to draw this little dotted line here. And I know that this angle here is 30 degrees. Let me write that a little better. 30 degrees. So this box is being pulled along the ground, but it's the applied force is at an angle of 30 degrees above the horizontal, right? So this box is being dragged across the floor. And let's say the box displaces a distance of 10 meters. All right, so this box is pulled over a distance of 10 meters, and let's say the mass of the box is 5 kilograms. And we just need to calculate the work done, right? So what is the work done on the box by the rope? So we know that the work is equal to FD cosine theta. We know he travels a distance of 10 meters. We know the force is 20 newtons. So we have here work is equal to 20 newtons times 10 meters times the cosine of 30. And that's it. All right. So we got 20 newtons times 10 meters times cosine 30. And there you go, 173. So 173 joules. All right. And that's the answer to that one. There really aren't any other problems that I need to go over. As you can tell, this is pretty straightforward. So I'm not shouldn't be particularly worried about this test. I know I was out for the last couple weeks, but I got a chance to glance at some of the class kicks, and it seems like people are getting the right idea. So anyways, if you have any questions, you can always email me. I'll be available after school as well to help out if you're feeling a little lost. And there's also a Pride block, but it seems like everyone's got a pretty good grasp of it. And especially after going through these problems, you can see that conservation of energy is pretty simple. At least it was a lot simpler than, say, doing some of the problems with forces in 2 dimensions. I know that test was not the easiest, but this is definitely easier than that one. So yeah, I hope that was helpful. And again, don't hesitate to email me if you have any questions or come after school for any additional help or Pride blog. But yeah, I have a good feeling that everyone's going to do pretty well on this test.